today I'm going to cover primarily preference optimization, and I think Aviral is going to cover some things related to reasoning. So let's get started. I guess like the one clear trend in the last 5 to 10 years has been that we've been like building larger and larger models, and we've been putting far more compute into them. This is like an very consistent trend. And if you're familiar with, or if you have like, some people are even making predictions about like AGI 2027, and they are like predicting that we're going to keep putting more and more floating point operations into these models. But the question today we're going to try to answer is, how do we get from like these large language models, which are pre-trained to predict text, and get these like really nice chatbots that some of them you might have used? So I'm going to very briefly talk about, this is not an NLP course, and you should probably like take one if you're interested in learning more about pre-training. It's a very, very deep topic. But I'm going to quickly touch upon what we learn in pre-training and why like that doesn't necessarily like translate into the kind of chatbots we use. So in pre-training large language models, they're trained on these gigantic corpus of internet texts. And the way they're trained is roughly predicting what the next word or the next token in the sentence is going to be. So for example, if you have a sentence, Stanford University is located in blank, California. So like the model will learn to predict what this text is. And you can imagine then you're learning to predict this text. You're learning a lot of facts, you're learning a lot of trivia, but you're also starting to learn something about the syntax of how like language operates. And we can look at many different examples here. Iro went to the kitchen to make some tea. Standing next to Iro, Zuko pondered his destiny. Zuko left so yeah, like the model will learn to predict the next token, which implicitly requires it to know some facts, know syntax, and also maybe even reason about what word should come next. While this may like predicting next token, you learn language, but predicting next token ends up learning a lot more. And there's some evidence that it ends up learning some notion of how the world operates. So this is a very nice example where we ask the model to predict the next set of tokens. And here the example is, Pat watches a demonstration of a bowling ball and a leaf being dropped at the same time in a vacuum chamber. Pat, who is a physicist, predicts that. And now the model is asked to predict the next set of tokens or the next set of words here. And to predict these next set of words, you implicitly have to understand what the text was. And in some way, you have to understand like how the world operates as well to be able to answer. And it's very interesting. Like if you change the prompt, like you'll get a different behavior out of the model as well. The point here being that language models don't just learn syntax, don't just learn words, but they learn a lot more about how the world operates as well. And similarly, like we can ask them to do math questions. We can ask them to generate code. We can ask them, they have like fairly like reasonable medical understanding as well. And more importantly, like we can start transforming these models into assistants now. So the question now we'll get back to is like, okay, pre-training gave us all that. So how do we actually make this into assistants? So today's lecture, we'll try to cover roughly 2 or 3 kinds of techniques to do so. First is instruction fine-tuning. Second is RLHF. And third is DPO. And then we'll talk about some limitations about what is missing, where are we going wrong, and so on. All right. So the first thing to understand is when we pre-train models, we're modeling language. And yes, that learns more than language. It learns something about the world, but that's still not equivalent to assisting users. So this is an example from GPT-3, where the prompt says, explain the moon landing to a 6-year-old in few sentences. And the model completes it with what it thinks should be the next set of tokens according to the distribution of text it has seen in its corpus. So it starts off, explain the theory of gravity to a 6-year-old. Explain the theory of relativity to a 6-year-old in a few sentences. And this is not what I expect my assistant to do. It's just a language model predicting the next token. What we do want it to do is actually give an explanation or a story where it like, a giant rocket ship blasted off the Earth carrying astronauts to the moon. So some kind of an explanation, which was the original intent of the question. and not just the text it has seen on the internet. And that's where the discrepancy arises between language modeling and assisting users. The first set of techniques that were developed for this was fine-tuning. And we're going to talk a little bit about this. So the general paradigm, even to this date, has been to first pre-train a language model on a large corpus of text and then fine-tune for a specific task. So how does fine-tuning work? You collect a set of inputs and you have some target outputs, and then you improve the log likelihood of these target outputs. So in this step 2, you have this input, which was the movie was something, something, and then you have some target output, which is good or bad, and the model learns to predict whether the output was good or bad. And that's really the main difference between fine-tuning and pre-training. As we realized, these pre-trained models are good for many more things, we started scaling up the number of tasks we can fine-tune on. So the previous example was maybe something like sentiment prediction, but really these models can be fine-tuned for many, many different tasks at the same time. So broadly, this can be seen as collecting a set of instruction and output pairs. So for example, if the instruction is, please answer the following question, what is the boiling point of nitrogen? We'll have some answer like minus 320.4. And we want to be able to predict this answer conditioned on the input. And once we collect a corpus of such instruction output pairs, we can then evaluate them on many, many unseen tasks. Can Geoffrey Hinton have a conversation with George Washington? Give the rationale before answering. And the model will produce a reasonable output here. So what if we fine-tune different scale language models on the same kind of corpus? So one thing that was observed in a lot of prior work is that as you increase the model parameter size, they actually start generalizing a lot better. So even taking like a very small corpus of such instruction output data sets, you start seeing a lot more generalization. So to explain the table a little bit, the Big Bench and MLU are like question answer pairs of the kind you just saw in the previous slide. And one thing to note here is that the bigger the parameters or larger the model is, the larger the gain is after instruction fine-tuning. So what this suggests to us is that the models start like responding and generalizing to questions even with like very small corpus of data as well. So to give an example of what the models look before and after instruction fine-tuning, it's a fairly simple question. In the following sentences, explain the antecedent to the pronoun and state that it is ambiguous. So you get something which represents more like the raw language model, which will start generating text on the right side. The reporter and the chef will discuss their favorite dishes and so on. But after instruction fine-tuning, it will give us what the user perhaps intended from the question, which is to give the correct answer. Cool. So instruction fine-tuning is fairly simple. There's nothing very complicated going on here. So I'll take a second. Like, do you see, just reflect for yourself. Do you see like some limitations to something like this? One limitation that obviously comes up is that it's expensive to collect such data. You have to collect questions and the labels for those questions. And that's hard. Like, as you start increasing the hardness of the questions, there's very few people who can answer those questions. So it's expensive to like scale such data collections where the humans have to sit down and write down the answer to every question. But then if you look beyond that, like there's certain tasks which don't even have a right answer. So and this is like a lot of the use cases of language models, like a lot of the use cases of language models are creative. So if I ask a language model to write a story about a dog and her pet grasshopper, there's no right answer for this. I cannot sit down and say, oh, this is the exact story I want to hear every single time a person asks this question. The second point is a little subtle, but in instruction fine-tuning, we have a predefined answer. So the mistakes are penalized equally. So there's no good or right answer. We're not necessarily saying like this was the mistake. We are basically saying your entire answer is wrong or your entire answer is correct, which is often not necessarily true for a specific question. So this is an example of this. If we have a statement like Avatar is a fantasy TV show, it's not that the sentence entirely is correct or incorrect, but it would have been better to describe the Avatar as an adventure TV show rather than a fantasy TV show. I think this is like a problem that has emerged recently, is that the language models truly are better at generating answers than humans. So if we rely on humans to generate the answers and generate the labels for our questions, we are going to be limited by how good the humans can answer the question. And finally, like one big mismatch is that LLM objectives, there's a bit of a misalignment between what we want our models to do, which is to engage well with humans, which is to follow their intent. Whereas our fine-tuning objective basically says, predict this answer really well. So there's a little bit of a mismatch in our training objective when we are doing instruction fine-tuning. Cool. So this leads us to the paradigm of reinforcement learning from human preferences. So the question is that how much of the improvement from instruction fine-tuning comes from following a format or actually teaching some new knowledge? I think most of the work suggests that it actually is teaching largely formatting. And most of the knowledge actually comes from the base language model itself. And there's a very clear way to do this. You can experiment this by just training the model wrong answers. And it still does quite well on the downstream tasks. So it tells us that it's actually teaching formatting more than the knowledge itself. The question are the corpuses always question-answer format because that's what we want out of chatbots? Not anymore. I think this was very early days of LLM fine-tuning and we were focused more on like question answering. But the corpus for instruction fine-tuning are very, very diverse now. These LLMs are used for a wide variety of tasks, function calling tools, and it's not just assistance means many different things. So it's not question answers. It could be just anything. Great. So now we'll get into reinforcement learning from human preferences, which addresses some of the limitations, which we discussed here. So throughout this section, we'll use summarization as an example because there's not necessarily a good summary that we can often train on. And for notation, we'll assume that we are given an instruction X and the language model will generate some sample Y, and we'll pretend that we have a way for a human to give us some kind of a reward score for a given summary conditioned on some input X and summary Y. So we have some news article, which is San Francisco, California, magnitude of 4.2 earthquake shook the San Francisco, blah, blah, blah. And we have one summary, which is earthquake hit San Francisco. There was minor property damage, but no injuries. And we have another one, which is Bay Area has good weather, but it is prone to earthquakes and wildfires. Clearly, one of the summaries is a little better than the other. So let's say our reward function gives us a score of 8.0 and the other summary gets a score of 1.2. Roughly speaking, we want to set up the objective such that we want to maximize the expected reward. So conditioned on some input instruction X, we want our language model to generate summaries Y such that the expected reward will be high. Fairly simple standard RL objective that you've probably seen in the class before. And this is the core of how chatbots are trained. And the rough pipeline looks as the following, which is from the Instruct GPT paper, is that we'll first do some instruction fine-tuning. We collect some demonstration data to condition, just to get the formatting right, as we discussed earlier. Second step and the third step, which we'll go a lot more into, is to set up how to first get a reward model, which allows us to align with human intent, and then we maximize the reward model. So these are the three steps we typically follow. Great. So let's just pretend for now that we have a reward model where we want to maximize this. And yeah, like I'm presuming you all are familiar with this gradient descent idea. So yeah, the way we would change the LM parameters to maximize this is something you've seen before, like some form of gradient descent. Usually there's like more complicated optimizers, but we can pretend that is not required right now. For now, we'll just assume like a generic RL formulation where we are generating some sample S hat. So for some distribution P theta S. We want to change the parameters theta such that the samples S hat are high reward under the reward function R. So the main issues, and this is why like we do RL, is like our reward functions are often non-differentiable. So if you ask me to give a number, my human mind is not differentiable. So we cannot back propagate through them. So this is why we resort to RL. So this is where policy gradient methods that I think Chelsea has covered like very early in the course come in, is that they allow us to maximize non-differentiable reward functions, and we can estimate and optimize this objective. And I'll do a brief recap here because it's important, and we'll slowly lead into the RLHF pipeline as well. But I presume like, you have seen this before. Great. So in this generic objective, when we want to estimate the quantity that we want is the gradient of the expected reward, where we want the samples S hat to have a high reward under R. So this can be written down. This is just algebra at this point, where the expectation can be written down as the summation of Rs multiplied by P theta S. And we have the gradient here. So this is just a definition of expectation. And now we're going to like propagate the gradient forward simply by linearity of the gradient. I assume you have seen this, but I'm going to go over this. But this is the log derivative trick, which is we can rewrite the gradient of P theta as P theta times gradient of log P theta. So to see that, this is simply from the chain rule, is that the gradient of log P theta simply can be written as 1 by P theta and gradient multiplied by gradients of P theta. Cool. So we can rewrite this as to get this identity where the gradient of P theta can be rewritten as P theta gradient log P theta. Cool. So the quantities in yellow is what we want to substitute back. And if we plug this back in, we get the following equation, which is reward of gradient of P theta is the same as expectation under P theta, R gradient of log P theta. All right. So why did we do all this? Typically, like when we're computing expectation over sentences, it's really not possible to enumerate every single sentence possible. It's just simply like intractable to even try to do that. So we want to be able to estimate the gradient somehow. And we want to be able to create some kind of a stochastic estimator so that we can get the gradient out. So this log derivative trick is what allows us to take this gradient and convert it into an expectation, which we can sample and then approximate. And this is what we get as a final result, is that it's again an expectation over reward multiplied by gradient of log P theta. So the question is, do we take this gradient because we cannot backpropagate correctly? There's two reasons really. Like, first is we cannot set up an objective where we cannot assume the reward is differentiable. Second, like, which is the more precise mathematical answer, is that our parameters are in the expectation. So we do need to figure out a way to take the gradients back to the parameters in the expectation as well. Yeah. But if our rewards were differentiable, we don't necessarily need to set our optimization objective like this. We could imagine other optimization objectives where we directly backpropagate end to end. Okay. So, so we went through all the math just to show that like we can rewrite the gradient of our original objective and we can rewrite it as an expectation again, which we can now approximate using Monte Carlo estimates, which is the equation on the end. And we can take this approximate gradient and plug it into our favorite optimizer, which uses gradient descent or ascent. And that's really like, this is just supposed to be a brief recap. So yeah. And it's a very intuitive objective as well. So, really all it's saying is that if for a certain sample, the reward is high, we should increase the log likelihood. So if you, the parameters are taking the gradient in the direction of samples which score high on the reward. And that's really all this objective says. And if it's bad, you like take directions opposite to those samples. Cool. And yeah, this is why we call it reinforcement learning, because we're doing good actions, go there, bad actions, don't go there. The question is, am I drawing full sentences or tokens? In this context, we'll be drawing full sentences. Yeah. The notation was set up generally, so like we'll go back to the XY notation again, but that was just supposed to be a brief primer on policy gradients. Cool. So, first problem is that like, we have so far assumed that we have some kind of a reward function which will tell us like, hey, like the summary is 10.0, the other is like 5.0. Like, that usually is not possible. Let's say you're training like the biggest and the greatest LLM possible, and it needs like millions of such queries, and we're not going to have a human army sit there and label every answer. So it's not very scalable to ask humans directly. So the general solution towards this end has been to make preference learning a separate optimization problem where we try to figure out a human reward model before starting our RL optimization. So, yeah. So we had two summaries and we pretended the score was 8.0 and 1.2. And we'll try to train on some kind of data where we try to predict the score so that we have a learned reward function, which we can later use in the RL. Okay. So we talked about like, we want to learn this reward model and we have some summaries where, like we want to be able to predict their score. So how do we like get these scores? So we need some kind of an annotated data set. Now the issue is that if we ask humans for scores directly, two different humans have completely different calibration. So for a summary that has a score of 7 would mean something completely differently to two humans. So there's not really an easy way to aggregate. And even for the same human, they would like probably score the same summary differently at different points depending on what they ate for lunch or something. So it's not really easy to get a score directly from humans. And if you ask them directly, it doesn't like work out very well. The reward models you learn are not very useful for training such language models. So the solution to this is to not actually ask them for a score, but to actually ask them for preferences. So we give them few summaries and we just ask them, hey, do you prefer this summary over this summary or not? And this is the kind of annotated data set we should expect to collect from humans. So now going a little bit deeper into this. So we are going to collect a data set of the form where we're given some kind of an input X, and we're going to be given some kind of a winning summary, which is YW, and we're going to be given some kind of a losing summary, YL. And we're going to have some data set D for this. And what we want to do is train a reward model, which assigns a higher score to the winning summaries and assigns a lower score to the losing summaries. So the optimization objective, which is called the Bradley-Terry objective, is a way of going from such data set of preferences to an implicit reward score, which would align with the preferences. And the way we train this is we minimize this log sigmoid and the difference of reward assigned to the winning and the losing summary. So, yeah. All this objective is saying is that a reward model should make sure the reward for the correct summary is higher than the reward of the losing summary. So the question is like, is it unbounded or do you normalize this? The actual issue that arises, this is actually a very important observation that we'll actually use to develop DPO as well. The objective just asks the difference to be high. So the difference will be high even if you assign a reward of 1,000 and 10,000, or it'll be high even if you assign a difference from 1 to 999. There's no real like scaling here which allows that. So yeah, typically you have to do some kind of post hoc normalization to make sure that different prompts get rewards at the same scale. Otherwise, like the optimization objective can get a little wonky. But yeah, this is the Bradley-Terry objective, which allows us to go from a data set of preferences to a reward model, which we'll use in RLHF. Yeah, the question is that why we take the sigmoid? Not really. There's a few different functions you can set up. Sigmoid just like maps naturally to like, the probability of this sample winning over this sample. So yeah, that's why it's typically used as a sigmoid. But really all we want to encourage is that the reward model should, like the difference should be high. All right. So now we get back to our RL loop, and what do we have? We have some kind of an instruction tuned model, let's say PPT. We have learned some kind of a reward model using the Bradley-Terry objective, which gives us a scalar output. So it takes an input X, gives us a summary, and then gives us a scalar output, RM phi X comma Y. Now, okay, so this is the simple part in some ways. We're going to do the RLHF loop here. And the way we're going to do this is we want to optimize the expected reward as we started with, where we're going to plug in our LLM parameters in the expectation for P theta. So it will produce some kind of a summary Y hat conditioned on some input X. And our reward model is going to be the learned reward model from preferences. Before I move on, like, I have a question which is slightly hard. I started off saying that the reward functions are non-differentiable. And that's part of why we want to do RL. But we just learned a reward model. And we know, like, we typically learn a reward model using neural networks themselves. And they are, like, very much differentiable. We can do back propagate through them. So why are we doing RL? That's the right answer. So, the token, like, we're outputting discrete tokens. And when we assume we can back propagate things, we cannot actually back propagate through the discrete language tokens. So even if we have a reward model that is differentiable, we generate some output, we plug it into our reward model, and then we want to go back directly to the parameters of the language model. But we get this discrete bottleneck in the middle where we cannot back propagate our gradients from the reward model to the language model. And that's the reason why, like, we again have to resort to RL, even though we have a differentiable non-black box reward model here. But yeah, good attempts, everyone. Like, these are close. Yeah. So let's say, like, we have a reward model, RM phi X comma Y hat. Let's assume, like, Y is a continuous variable, or like, so typically we'll take some input, we'll generate some output, we'll plug it into a learned reward model. And if everything is a continuous function here, you can rely on back propagation to take the gradients and update the model parameters such that the reward model score keeps going up. So you don't actually need to do RL. And not doing RL is often very good because it's expensive to do because of the sampling. But the issue is that our Y hat here are discrete tokens. So they're sampled from some underlying distribution. And once you include the sampling operation, it's very hard to, like, there are tricks to do that, but they're not very stable. But it's hard to, like, back propagate through there. Yes, so I didn't want to assume, like, Gumball softmax is known to people here, but, like, Gumball softmax, unfortunately, like, so far hasn't scaled super well. Especially, like, now the language. So to contextualize this, Y hat is a sentence which could be thousands and thousands of tokens, and each token vocabulary sizes are on the order of hundreds of thousands of tokens. So it's, yeah, the entire sentence is a combinatorial space of like 100,000 tokens multiplied by the sequence length. Gumball softmax usually doesn't scale beyond like 1,000 dimensions or so on. Yeah. Cool. This is a hard question. So I wanted to like touch upon this because you should never assume that you need to do RL. So yeah. All right. So, one issue, like even when we set up this objective is that, and somebody alluded to this, was that our reward models are never perfect. So we don't want to assume that like they'll give us a perfect score. After all, they have been like fit to human preferences on a certain distribution. We don't want to assume that they'll give us a good score for every single input and output. So, and if you do naive optimization like we described so far, you will get models which hack the reward model, and we'll see some plots for that later as well. So another thing we add is something called the KL penalty, or the callback library divergence. And what the KL penalty basically says is, so it's added to the reward where we have beta log p theta by p pre-trained. So p theta is the quantity we are optimizing right now. This is the language model, which is currently assigning the probabilities to token y hat. And p pre-trained is the model we started with. So it could be instruction fine-tuned, and these are the probabilities under those models. And roughly speaking, whenever a probability distribution deviates from the pre-trained distribution, we get a penalty. So we get a lower score if we are deviating too much from the pre-trained model. And if you work out the math, this thing is exactly the KL divergence between our distribution or our language model that we are optimizing right now and the language model we started with. And the reason why we want to do this is that, as I said, like the reward model is imperfect. We know it's more accurate on a distribution of preferences that we trained on, and we want to make sure the model stays close to where it started off from. So this was one of the first examples of like RLHF where it worked quite well. So this is the summarization task itself. And the curve basically, the x-axis is the model size, and the y-axis is how often is the summary preferred over some ground truth summary for some news articles. And if you look at the blue curve, it's the pre-training curve, which as the model size increases, the fraction of summaries preferred over the baseline increases. And then you have SFT, or instruction fine-tuning, which gives an improvement over the pre-trained model. But when you look at the RL curve, this is the first model which actually exceeds the human written summaries. So now we are generating summaries even at a small size, which are preferred over human summaries. And this is like one of the earlier results in RLHF, which shows like the power of optimizing for preferences directly. So the question is like, are there models for human preferences which are not just binary and like account for like fuzzy? I think this is a very like hard question, which like goes into, so it is known that human preferences can often be intransitive. So what do I mean by that? Is like, let's say we prefer A over B, then we prefer B over C, and then we prefer C over A. This doesn't make any sense. Because ideally, if you prefer A over B and B over C, you should prefer A over C. But we get lots of scenarios where humans prefer A over C as well. And you will unfortunately observe some noise in the data like that, where the preferences, in fact, the preferences we observe in real life are like very, very noisy. And I don't think we have like a great solution for this. To like even ground this, preference learning is a binary classification task. We're just trying to predict like which sample is winning. So it's a binary classification task. So you like most binary classifications, you can reach an accuracy of like 90%, 95%. But for most of our language model and reward models, we reach an accuracy of like 65 to 70%. So we're barely doing better than chance. But even that is still like enough to like give us like pretty large improvements in performance. The question is like, what changed to make this differentiable? We did not make anything differentiable. That's the reason why we started doing RL, is to like be able to take the policy gradient. Like this estimator, this does not require us to be able to, So that just requires the gradient to be like with the log probabilities of the model. It does not backpropagate into the reward at all. So the question is like, what if the P theta RL is less than P theta PT, and like, wouldn't that encourage the model to go in those directions? It's good to know. So this is like the expectation is broken down here into more explicitly, but it's good to know a property about KL divergence that is always greater than equal to 0. I leave that as an exercise for you to like prove that, but like, so the penalty is always positive. So the question is, are there intelligent ways to choose prompts such that we get preferences over things that the model is bad at? That's a great question. Yeah, like, so there are works which try to look into it. This like touches upon active exploration. You want to get preference signal explicitly where the model is confused, right? So I think there's things which touch upon like, we want to maximize information gain such that the model will learn the best. Is there a well-established standard? I don't think so, but this is like a good problem to look into. Okay, I will start with direct preference optimization next. So if there'll be a little bit more math, but it's very fun. So we're going to talk a little bit about direct preference optimization. So the RLHF pipeline I described, some of you might find it complex or some of you might find it easy, but in practice, when we try to do this at very large scale models, it can be quite expensive. So let's say you're like training 100 billion parameter model, maybe a trillion parameter model. You have to sample every answer and then query a reward model. And depending on the RL algorithm you use, you have to compute like value functions and like other things just to optimize the model. And you don't have to understand this figure. I put it specifically to scare you guys. So here, like, there's just like a whole flow of things that in practice can be fairly hard to get right. And the more parameters you have in the system, the harder it is to get it right. So RLHF can be pretty complex, but so when we were looking into direct preference optimization, our goal was to like, can we like make this a lot simpler? And yeah, as I said, like they have some initial pipeline which we fit in RM. We like take an instruction tuned model and produce a final RLHF model. But if you look at the whole process, like we have a language model and we're collecting some preferences. Why can we just not directly like train on the preference data and directly optimize the parameter models? Why do we have to like learn this like intermediate quantity like a reward model? And why can't we just directly go from preferences and optimize our language model? So that's really why it's called direct preference optimization, is that we find a way to go from preferences to and optimizing the language model. And the way we do it is that at a very high level, we want to be able to write the reward model in terms of our language model itself. Why do we want to do that? Because we fit our reward model to the preference data through a fairly simple classification loss, the Bradley-Terry loss we discussed. If we can just connect the reward model and the language model, instead of like having a separate process, we can just take the language model parameters and fit it to the loss through the loss directly. And that's really like the high level motivation for direct preference optimization. Yeah. So this part of the math gets a little bit slightly intense, so like I'll go through this slowly. Okay. So we discussed the scale constrained RL objective in the last few slides, where we want to maximize the expected reward with some KL penalty such that the model should not drift away from the instruction fine-tuned model a lot. So this, again, the parameters we're going to optimize is P theta RL, P pre-trained and RM are fixed. And for now, we can like, yeah, we're just assuming some kind of a reward model here. It turns out that this equation actually has a closed form solution. And this is not possible if you're doing just the regular expected reward maximization. But once you add a KL constraint, it turns out that you can write out a closed form solution to this equation, which is really cool. Like it's rare to find such things. And the solution looks something like this. This is the optimal policy. P star, we're going to compute probabilities over Y hat conditioned over X. And roughly this optimal quantity says that we want, ignore the ZX for now. We have our pre-trained model, P pre-trained Y hat given X, and we're going to multiply the log probabilities with the exponentiated reward. So what, very simply put, like exponentiated, so if a sentence has a higher reward, so if a y hat has a higher reward, we're going to upweight the probabilities under the optimal distribution by an exponentiated reward by beta. High reward, high exponent, higher probability under the optimal policy. If the reward is low, it's going to be downweighted by exponential reward as well. And Zx here is just a normalizing factor, which ensures that this quantity is a probability distribution. So really, you only need to focus on the numerator, and that's it. You'll have to take my word for that this is the optimal solution for the above equation. Maybe I can share something later on, like how to derive this. But yeah. Cool. Now, this is like where the key observation comes in, is that because we have this optimal solution to the above equation, we can rewrite the reward model in terms of the optimal policy itself. So this lower equation is just like a rearrangement of the terms. The reward model can, Rm x comma y hat can be written as beta log p star upon ppt. And we have some beta log zx term, which is a constant over y. So again, just to like make sure this makes sense intuitively as well, if a completion y hat should have a high score, it will typically have a high probability under p star as well. And ppt is something that's fixed, so beta log will be high whenever the reward model gives a high score. And similarly, like if a reward model assigns a poor score to y hat, our optimal policy will typically assign a low probability to y hat, and typically the beta log p star by pt will also be low. So the relationship sort of makes sense, and we can ignore zx for now. Cool. The main argument here is that this isn't just true for the optimal policy. You can always plug in some reward model p theta, and it will be optimal for some kind of reward model. And that's really like the observation you make here. And yeah, so we've just replaced p star with some kind of a learnable policy, given that our parameters theta represent the optimal policy for some kind of a reward model. And after that, it's simple. Like, given the relationship we have derived so far, we know this is how we fit our reward model through the Bradley-Terry laws, where we want to make sure that the reward for the winning completion is higher than the reward for the losing completion. And so far, I've been asking you to ignore the partition function, but that was for a reason. The reason is that because the objective only optimizes for the difference between the rewards, the partition function zx just simply cancels out. So maybe I can write this out on the board. We started with the relation Rm theta x comma y w, and we had beta log p theta y w given x, where y w is the winning completion, and p pt y w given x. Yeah. So this is the relation we used with beta log zx. And we're going to rewrite the same thing for the losing completion as well. So x comma y l beta log p of theta, which is the current parameters we're optimizing. YL is our losing completion, conditioned on the input x, divided by the log probabilities under the pre-trained model, YL, conditioned on x, and beta log zx. Now notice that like the reward model is like, the input is the same to the reward model. So we're using the same text and we're summarizing the same text. So the input is actually the same. So when we're going to subtract this, we're going to subtract these and this is just simply going to cancel out. The reason why canceling out of this is important is that zx is actually intractable to compute. It's not something we can compute for real. So we get this relation that you can see over here is The difference between the reward models is simply the difference between the beta log ratios here. Cool. So taking this identity, which we have just derived, we simply plug it into the original Bradley-Terry loss, and we get something super nice, is that we'll have a data set of, again, input, winning output, losing output, and we're going to optimize this objective directly for the language model parameters. And this is a classification objective, by the way. So we're not doing any RL loop anymore. We are going directly from the preference data set and optimizing the language parameter models themselves. Yes. So initially, they'll be the same, but the gradient would only backpropagate through the p thetas. PPT will remain the same throughout, and it will increase the probability of the winning completion and decrease the probability of the losing completion. So let's spend a little bit of time here again. This objective will try to encourage the RM theta for the winning completion to go up and RM theta for the losing completion to go down. By the way to increase RM theta is to increase the probability of YW under the current model and decrease the probability of the losing one under the current model. It's a very intuitive objective, right? Like good thing go up, bad thing go down. And apparently you can do it without RL or any complexity. And so the question is, can we do something like distillation without, instead of this? The question is so for the reward model, you first have to get a reward model somehow, right? There's no easy way to get it. So you have to collect some kind of preference data to even begin with, to get a reward model. And that's where DPO comes in, is that if you have collected a preference data, instead of fitting an explicit reward model, you can optimize your language model parameters directly. Yeah. So the question is there's a penalty for pre-trained model with not drifting too far from the pre-trained model. Actually, this does do that. So this is a good question. So our loss function is set up as a log sigmoid. So one property about the sigmoid is that the gradients vanish when the difference is already sufficiently large. And the difference becomes sufficiently large, faster than so the beta parameter actually controls how quickly the difference becomes large. So if you have a very high beta, even a small discrepancy would suddenly saturate the sigmoid and it will not change the parameters a lot. The question is the main advantage of DPO that you don't have to train a reward model? The way I would say it is that you are training a reward model because you're using the same objective. The DPO provides a connection between the reward model and the corresponding optimal policy for it. So you don't have to do an explicit RL loop to go from the reward model to an optimal policy for it. We have cleverly parameterized a reward model in terms of the language model itself. So when you fit a reward model to the preference data, you are optimizing the language model itself too. So the question is, do we still need to do RLHF or not? Given this is cheaper. I think it depends a lot on situation. I think there's still some purported benefits to RLHF because you can expect some kind of generalization from the reward model, which allows you to grade generations which might not have been seen in preference data. So there's still some benefit to it. So it depends upon your budget and what you want to achieve. So the question I get is that the KL divergence, why are we relying on the sigmoid when initially the KL divergence was not related to the sigmoid? To be more clear or precise, I think it's the beta term which controls how much you're allowed to drift away. And even in the original RL objective, this beta term is what controls the allowed divergence between our current model and the pre-trained model. So if the beta is really high, you are not allowed to diverge at all because you'll be penalized a lot more. Yes. So the beta controls the strength or the weight on this divergence. That's a good question. Yeah. So there's two kinds of sampling involved right now. first we want to like create a preference data set where humans label their preferences. And then during the RL optimization itself, we want to sample to get a score under some kind of an external or like explicit reward model. And then we score and then we optimize. So we are taking care of the second sampling step, but the first sampling step is still needed. Yeah, that's a good question. So when you're doing online RL or like some kind of RLHF procedure, you don't only need the prompts. You don't need a preference data set. So typically the set of prompts which is used during RL is larger than the set of prompts you use during preference training. Yeah, that's a good question. So like, I think the question basically tries to ask like, can we take into account the strength of the preference and not just like a binary label? I think this is a limitation for both RLHF and DPO, I think. And we should, so giving more insight, typically like when we collect preference data sets, we ask annotators to like give a strength for their preferences, and we only keep the preferences which are strong. So typically but this isn't a resolved problem. How to learn from noisy data and like low preferences or high strength preferences, like still an undersolved problem. And yeah, like these are some of the results for direct preference optimization. We showed like a theoretical equivalence between doing the DPO objective and doing a KL constrained RL procedure. And in practice, when we try to look at the summarization task and try to measure win rates like we were doing earlier, we do actually find that like it does similar or better, but this is like a debatable question. So like, yeah, but like in general, it does pretty well. The beta parameter that, do you see this beta parameter here? That corresponds exactly to the beta parameter which is the extra hyperparameter there. So I'm just going to summarize like what we have learned so far. And then we'll move on to like where things are missing and so on. We want to optimize for human preferences because, first of all, it's like more aligned with the objectives we want. The way we use these models are more closely aligned with like improving human engagement or like satisfying human preferences. So we want to optimize for that directly as well. And instead of relying on uncalibrated scores from different annotators, we try to collect preferences and then learn a reward model of some form, either through DPO or through RLHF, and improve the model through that. In RLHF, we learn an explicit reward model, which gives an explicit score for every completion we sample, and we use that to optimize the language model parameters. And we typically impose some kind of KL constraint to make sure that our model does not drift too far from where it was initialized. It's very effective, maybe sometimes even more effective than DPO, but can be a little tricky to get right, and it's computationally expensive because of the sampling procedure that needs to be done. And in direct preference optimization, we can completely skip the sampling part and optimize directly on the preference data by posing it as a binary classification problem. Cool. And it's very simple and effective and does not require an online step. So where does this all lead us? Like, we have like discussed all the RLHF and DPO stuff, and like these are roughly how the chatbots are built, by the way. So this is the Instruct GPT pipeline. This was like one of the first like first chatbots which was available to public, and they interacted with it, and it worked pretty well. Like it can do a lot of tasks. It can answer general purpose questions, and yeah. Instruct GPT, like, this is a comparison between what the pre-trained model gives as an answer versus what an instruction tuned or an RLHF model gives as an answer. And yeah, these are some examples. And yeah, we have optimized these models for dialogue, and like it's not just summaries, I want to say, like, we can optimize them for many, many general purpose tasks. And the more data you collect, more tasks you cover, the better these models are going to do, the better they're going to understand the intent, and the better they're going to like respond to like all of our needs. And yeah, DPO has been used a lot in the open source community ever since it was launched. It's fairly cheap, works, it's pretty performant. And at some point, like, all LLMs were using DPO to like get their alignment with human feedback. Llama and Mistral models, if you've heard of them, were also like post-trained using DPO. So yeah. And I guess like this is an interesting example where it's a good question to ask. Like, what is the difference between instruction tuned model and RLHF models? And like one clear stylistic difference that emerges is that they tend to give more detailed answers, well-formatted answers, and they tend to like align more with the kind of text that humans find easier to read. So the question here are like, what are the 5 most common causes of stress among people? And if you just do instruction fine-tuning with a very small data set, you get a good answer. The 5 most common causes of stress among people are work, money, relationships, health, and family. But then you do some kind of a PPO procedure, you get a much clearer, longer answer with like a very well-formatted list. And these are all emergent properties. This is what the model has discovered that humans like and prefer, and that's why they tend to generate answers of that form. I love the question. I'll basically like, I had a slide on this towards the end. But yes, the question is like, can we trust like people's feedback? And what do we do if like people don't know what they want? Again, that's a very like hard boundary to go to. And I think what happens is that like there's a misalignment between short-term incentives and long-term incentives. There's certain behaviors which look good in short-term and people give feedback based on short-term incentives. But sometimes these are very undesirable in the long term. And that is truly an hard problem to solve within the RLHF pipeline. That's a good question. The question is like, do they rank like 2 answers or multiple answers? And do we train on NC2 pairs or, yeah. So I think like, yeah, you can roughly like just for efficiency purposes, people typically rank more than 1 answer and you get more learning data out of it that way because you get NC2 pairs, preference pairs. But there's something called the Plackett-Luce family, which is like a generalization of Bradley-Terry that allows you to directly train on ranked completions as well beyond just preference pairs too. So you can do either of those. They probably both work fine. Yeah, that's a really good question. So I think like our company's incentivized to like give preferences to like engagement, which are not aligned with human. This goes well beyond the scope of this lecture and like be like, I don't know, like what I can say about this, but we can look back at history, right? So this is not an issue that was just true for LLMs. For example, YouTube had a lot of issues with like recommendation systems and people were engaging with YouTube way more than they wanted it to. So in some ways, like this is a broader problem, which like on how technology should be interfaced with people and societies. But if I briefly recall from that incident, is that it was actually in YouTube's incentive to make sure that the consumers have long-term healthy engagement. So, which means like, if they're like spending 20 hours a day on YouTube, that's probably not good for the product as well. So they probably want to make sure that they're not spending way too much time. So if you do optimize for long-term engagement, that should not fall to like the sycophantic behaviors that we saw from GPT-4o because that is more short-term behavior. But yeah. Cool. And yeah, like, this is basically all we've talked about. And I wanted to bring up like a couple of things that let me just jump ahead to this slide because we've already talked about it, is that this is a very like fast evolving topic. This is touching our lives right now when we are deciding how like to interface chatbots with humans. And for people who might not be familiar with this incident, but like GPT-4o became fairly sycophantic due to a model update that was pushed. And suddenly it was like endorsing all good and bad ideas from their users in a way that everyone deemed was unhealthy. So I don't work at OpenAI and I'm not making any comments, but like, there's issues like these are very real and we're still trying to understand how does our feedback data affect our final model's emergent behaviors. And this like affects how we use our products as well. And yeah, like a lot of great questions came up in the class and those are like active problems people are working on and we don't necessarily have the answers to all of them. So you guys should go look more into it. Yeah, and the other main thing that I do wanted to touch upon, like, which is a limitation of the current paradigm, is that there's this phenomena of reward hacking, which again touches upon misalignment as well, is that when we train on these learned reward models, they do align with human preferences up to a certain point, but as you train progressively against them, they tend to start drifting away from what we truly want. So it's a very common problem in RL when you have proxy rewards instead of true rewards that you care about. And this is generally true for machine learning as well. So yeah, this affects our ability to scale reinforcement learning too, because if you start hacking, you have to stop training at some point. And this is like an active optimization problem that people are trying to address. Yeah, I think the field is evolving quite a lot. So like it goes beyond like people are moving towards more rubric-based things where we score them for several different aspects. But yes, like you typically do want to collect many different kinds of data to teach the model like what kind of behaviors we want to instill and what's the right way to respond to certain situations. It's very hard to cover every situation a chatbot might ever encounter. So we are relying on the model to generalize from what kind of data we're teaching, but these things break all the time. And there's certain unexpected behaviors that come out of these models, in ways where we could not anticipate. Yeah, I've already touched a little bit upon this, but like it's a very fast evolving field, very like many areas still to improve. Preference data is still expensive to collect, and like as we have maybe discussed, like it's not necessarily like representative of what kind of model behaviors we want. So we are looking for better ways to like improve the feedback. I think you listen to a lot more about very cool evolving things in reasoning space, where the models are generating their own outputs and are being graded by verifiable rewards. And that's like one of the coolest topics we're looking at as well in post-training and reasoning as well. And something that I personally find very interesting is that like language models are aligned to the aggregate preferences of humans, but like we are interacting one-on-one. Like we're not interacting with the entire internet. So we do want to eventually make sure that the models are aligned to our needs and not just everybody's needs. So personalizing language models and having more contextual input about us and our preferences is something that's also a fairly nice evolving field. And yeah, we talked a little bit about hallucinations and like uncontrolled emergent behaviors. And these are all still active problems we like work on. And that's all for today.